Okay, so we're going to run the gas and gas stoichiometry assignment over 3 videos because there's 9 different types of questions here. Now the first type of question is going to be a Boyle's Law question. It's going to ask us what's the final pressure if in the container if 965 milliliters helium gas at 173 millimeters of mercury is compressed to 236 milliliters. Okay, we're going to assume the temperature and the amount of gas are held constant. Okay, so this is going to be a P1 V1 equals P2 V2 question. So we solve for P2 because we have V1 and P1 and V2 here. So P1 V1 over V2, let's just set this up, 173 millimeters of mercury times 965 milliliters divided by 236 milliliters. Because the units cancel out on the milliliters, we don't need to convert these into liters, and we're just going to leave the answer in millimeters of mercury, so we'll get 707 millimeters of mercury. There's no need to convert to atmospheres. That conversion factor would wash out in this conversion. Okay, so for question type 2, what we're going to have here, let me turn the light on just so we get a little extra light here. This is going to be a Charles's Law question. To what Celsius temperature must 28.7 milliliters of methane gas at 77 degrees Celsius be changed so the pressure will be 70.9? So the volume, I should say volume, will be 70.9 milliliters. Assume the pressure and the amount of gas are held constant. Okay, so V1 over T1 equals V2 over T2. Okay, so what do we have here? Well, we have V1 and T1, and then we have V2, so we want to find T2. Well, to find T2, we have to rearrange the equation. We have V2 over V1 times T1. Now, unlike the previous question, where we could just use the units as given, when we deal with temperatures in any gas law question, we have to convert the temperature to Kelvin. So the first thing we need to do is take that 77 degrees Celsius and add 273 to it to get it into Kelvin. So that takes us up to 350 Kelvin. So now we can just plug and chug our values in. 70.9 milliliters divided by 28.7 milliliters times 350 Kelvin. Okay, that's going to give us 864 Kelvin. But note, the question wants us to give the answer in Celsius. So now we need to subtract 273 from this answer, and that gives us an answer as 592 degrees Celsius. Okay, so let's go on to question type 3. Question type 3, what is the volume of 181 milliliters of oxygen gas at 18.6 degrees Celsius and 311 millimeters of mercury if the conditions are adjusted to 375 millimeters of mercury and 122 degrees Celsius? Assume the amount of gas is held constant. Okay, so we're going to hold N constant. We can solve this 2 ways. We can take the ideal gas law, PV equals nRT, and solve that twice, find N, and put it back in for the next temperature, or just combine Boyle's and Charles' law. Well, if we combine Boyle's and Charles' law, we don't have to deal with an R constant. So P1 V1 over T1 equals P2 V2 over T2. Well, now we have to ask ourselves, what do we have going on here? What are we solving for? Well, we have V1, we have T1, we have P1, we have P2, and T2. So we're solving for V2. So V2 is going to be P1 over P2 times T2 over T1 times V1. Alright, we don't need to convert the pressures, but we still need to convert the temperatures. So T1 equals 18.6 degrees Celsius plus 273 Kelvin gives us 291.6 Kelvin. T2 equals 122 degrees Celsius plus 273 Kelvin gives us 395 Kelvin. Now all we gotta do is plug and chug. 311 millimeters of mercury divided by 375 millimeters of mercury times 395 Kelvin over 291.6 Kelvin times 181 milliliters. Kelvins cancel out, millimeters of mercury cancels out, our volume will be in milliliters, and it turns out to be 179. Oh, sorry, wrong answer. 203 milliliters. Okay, so does this make sense? Well, temperature increased, so the volume should increase a little bit. In that particular case, the pressure decreased, so the pressure increased, and we would expect to see a little bit of a volume decrease. So it's not a dramatic increase, but it's still something that we would expect to see. Okay, so let's go on and do question 4. Question 4. What is the volume in liters of 81.6 grams of CO2 at 322 millimeters of mercury and 226 degrees Celsius? This type of question, we have to use PV equals nRT. We're solving for volume, so we have nRT over P. Okay, well, we need to find N, and we need to convert pressure to atmospheres and temperature to Kelvin, because R is going to be 0.08206 LATM per mole Kelvin. Alright, how do we get N? Well, we take 81.6 grams of CO2, divide that by 44.01 grams per 1 mole CO2, and that's going to give us 1.85 moles of CO2. 322 millimeters of mercury divided by 760 millimeters of mercury per 1 atmosphere gives us 0.4236 atmospheres. Temperature will be 226 degrees Celsius plus 273 Kelvin gives us 499 Kelvin. Okay, so we take V equals 1.85 moles times 0.08206 LATM all Kelvin times 499 Kelvin. Divide that by 0.4236 atmospheres. The volume ends up being 179 liters. Okay, so that's all we have to go through and do for that type of question. Question 5 is very similar. Okay, what mass of sulfur trioxide gas, SO3, will occupy 598 milliliters at 942 millimeters of mercury and 69.6 degrees Celsius? This is another ideal gas solution. PV equals nRT. This time we're solving for N equals PV over RT. Well, we need to get pressure in atmospheres. 942 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury, which gives us 1.239 atmospheres. The volume is an easy conversion. We take the 598 milliliters, divide that by 1,000 milliliters per 1 liter, and that gives us 0.598 liters. Temperature is going to be 69.6 degrees Celsius plus 273 Kelvin, and we're going to have 342.6 Kelvin. So we solve for N. 1.239 atmospheres times 0.598 liters divided by 0.08206 liter atmospheres per mole Kelvin, and then we multiply by 342.6 Kelvin. That gives us an N of 0.02635 moles of SO3. All we have to do from here is multiply this number by the molar mass. Well, if the molar mass is 80.06 grams per 1 mole SO3, the mass is going to be equal to 2.11 grams SO3. Okay. Question 6. What is the density of ethane gas C2H6 at 942 millimeters of mercury at 52.9 degrees Celsius? In this particular case, we need to use the equation from the book to find density. So density is equal to pressure times the molar mass divided by RT. So we need to get the pressure in atmospheres, because R is still going to be our 0.08206 liter atmospheres per mole Kelvin. We need to find the molar mass and the temperature. So the pressure is going to be easy. 942 millimeters mercury divided by 760 millimeters of mercury per 1 atmosphere gives me 1.239 atmospheres. Temperature equals 52.9 degrees Celsius plus 273 Kelvin. That's going to give me an answer of 325.9 Kelvin. The molar mass, we simply just take 2 times 12.01 plus 6 times 1.008, and that turns out to be 30.07 grams per mole. Alright, now let's plug in chug time. 1.239 atmospheres times 30.07 grams per mole, divide by 0.08206 LATM mole Kelvin times 325.9 Kelvin. Alright, atmospheres cancel out, moles cancel out, Kelvin canceled out. Our units are going to be grams per liter. So we end up getting 1.39 grams per liter when we throw this into the calculator.